Okay, so we have looked at equilibrium qualitatively for quite a while. Let's get down to equilibrium calculations, which we will see a lot of over the next few lessons. So let's use this sample question with this sample reaction. Hydrogen gas reacts with fluorine gas to give you HF gas. Notice first what the states of the reactants and the products are, and eliminate any solids or liquids because they don't contribute to the equilibrium due to their constant concentrations. So in this case, all of them are in the gaseous state. That's great. The Kc of this reaction is given as 1.15 times 10 to the power of 2. You might be wondering why not use Kp. We could use that, but if the question gives us Kc, use Kc. After all, the concentration is just the number of moles over the volume of the system. So Kc, again, recalling the equilibrium expression, is Hf squared over H2 and F2. Why squared? Because we raise each concentration to the power of its stoichiometric coefficient. What other information has been given to us in this question? It tells us that 3 moles of each reactant was added to the vessel, which is of volume 1.5 liters. So we can find the concentration of H2 and F2 initially at the start of this reaction. That gives us 3 divided by 1.5, which gives us 2 molar. Great, so we now have the initial amount of concentration of reactants, and the equilibrium ratio of reactants to products. Now what? We're stuck. You know that the concentration of the reactants will decrease and the concentration of products will increase. But by how much exactly? You have the ratio, but how exactly does one use it to calculate the equilibrium concentration of all the products and reactants? Don't fret, here is where we pull out a convenient tool for calculation. That is the pencil, not the calculator, which we will deploy later. In equilibrium calculations, we use something called the ice table to visualize the changes in concentrations of a system from its initial state to its new equilibrium. We represent it like this. I stands for initial concentration, C stands for change in concentration, E stands for equilibrium concentration. Each column exists for one reactant or product, and we like to put the reactants on the left and the products on the right for ease of use. So let's start filling up this table. Let's go row by row. Initial concentration. We know the initial concentration of H2 and F2, so let's put 2 molar inside these 2 boxes. As for HF, at the start there is no HF because no reaction has occurred yet. So HF concentration initial is 0. Next, let's look at the change in concentration. How much did the concentration change by? Well, if you knew then you would have already gotten the answer to the question, wouldn't you? We don't know. So let's leave it as X. Negative X rather, because the concentration of H2 and F2 is reduced. As for HF, because for every X mole of H2 or F2 consumed, I produce 2 moles of HF, the increase will be 2 plus 2x. Finally, the equilibrium concentration. Again, we don't know this, so let's just add the initial concentration and the change in concentration to find out what the equilibrium concentration ought to be. For H2 and F2, it will be 2 minus x, that is the equilibrium concentration. For HF, it will be 0 plus 2x, which gives you 2x. How does this solve the problem? Now let's look at your equilibrium expression again. What you have there is the equilibrium constant. What you have on your table are the concentrations for calculating the equilibrium constant. So just substitute the concentrations inside this expression. And here's the moment we are all waiting for. Take a moment to pull out your calculator or go to Wolfram Alpha to solve for your x. Otherwise, you can always expand it and apply the quadratic formula, which we are not going to do. Please use a calculator. And after some mathemagic, x is 1.69. So we can now find the equilibrium concentrations of H2, F2, and HF. H2 and F2's equilibrium concentration is 2 minus x, which gives us 0.31 molar. And for HF, it is 2x, which gives us 3.38 molar. And that's how you go about solving an equilibrium calculation problem with an ice table. We will have more examples over the next few lessons, so make sure that you are well acquainted with the idea of the ice table.